Well, hello everyone. Welcome back to the part 2 of me coding a simple production style C++ application for Windows only using Win32. Now in this application we are doing a simple task of removing a binary file digital signature. Now watch the first part if you're curious, how we started everything. We basically coded simple scaffolding for error handling and just started the removal of RemoveDigitalSignature function here that opened the file for reading, and that was pretty much it. So at this point, like I told you, this is very important because we're talking about production style application to handle errors. So since we created our function here, we start using it. So obviously in this case we need to provide getLastError, and getLastError will get us the error from create file, which will tell us what the problem was. And then we need to specify a little bit of a message for the user to tell them where exactly the failure happened. So I kind of like go with very simple laconic kind of descriptions. So in this case we would say failed to open binary file, and then we will specify which file, right? So that the user can see if there's a typo in the path or if there's something else. Now this error will be most certainly and most often displayed, in case user specified some file which our function cannot open. So make sure to provide really nice description here and don't go too much overboard with it. But again, this is very important to handle every error situation. Now in this case there is no logging, it just simply outputs it to the user. But because we created this little helper function for us, it will actually give us some very needed ease of use for them. Let's put a little bit of spacing here. I kind of like to separate visually. Okay, so in this case we opened our binary file, but we need to do a couple checks. First, let's get file size. Now I'm going to use newer API, get file size X. Well, newer meaning from Vista. I guess it's not new anymore. It takes file size and it takes the second parameter, which is a large integer, pointer to a large integer. So we need to create it first, and let's say li file size. I usually null it out and do it like this. Again, the API can fail. Make sure to always check for failures. Again, this is very important in production application. Don't just leave it dangling, because if for some reason this API did not return an error code for you, and did not succeed, the user will have no idea what happened. So in this case I'm going to copy this thing here, and I would say fail to get file size. Now the odds of this happening are low, but still keep in mind that any API, if it can fail, it may fail on some system. So make sure to provide kind of a nice and easy to understand explanation for yourself if you are logging, or for the user. Okay, so we got the file size, which we will need later. Then we need to make sure the file is not too large. Now the user can technically provide any file for us here, but it has to be within certain size that our program will work with. So in this case I would use quad part, and it has to be less than int max. Now the odds of a P file being that huge are low, are pretty slim. So at this point we will not handle really large files. So in this case we need to output an error as well, guys. Keep in mind this is very important. And what you can say is that file is too large. Now there is a little bit of a problem here because we cannot use get last error because we don't have last error. What we have is just this condition that didn't work for us. So how do you handle this? Well, in this case, we need to find our own error code that will be output to the user. Now you can technically do like -1 or 0, but this is not very user-friendly. So what I like doing, I like using my own tool, which is called WinAPI Search, and I like to search for error messages. So I would use word large. Let me like expand it a little bit, and I will search. And then I would see which one kind of fits, the description fits what I want to do. Like this one, the specified object is too large, seems like what kind of fits here, and I will use it. Okay. Now I don't have to use any specific like definition for it. All I care is just that it matches the code. This is what I wanted to see here. Okay. So this is how we check file for being too large, and that's how we can also output a reasonable error message for the user. Again, this is important so that people that use your application don't just say like, oh, it just showed some weird error and we don't even know what it is. By providing a meaningful statement for the user, you are creating a very sensible and very smart application that people will use and like. There is one little check we need to make sure here, because this quad part is actually long, which means it's a signed integer. We need to explicitly cast it to unsigned one. So in this case, if it's a negative value, like a really large file, which is highly improbable, but just in case, it will not satisfy this condition. Okay. So now when we have a file size that we know is less than int max, and int max is basically a largest signed 32-bit value, which is what we needed, we can reserve memory for the file data. Now I'm not going to, I'm going to go the easy route and just load the whole thing into RAM, the whole PE file into RAM, even though we don't need the whole thing. We just need the header in the end, but it just makes it simpler to do it this way. If the situation happens when I have to load, when the file becomes too large for being loaded in RAM, in that case I will probably have to break it up into chunks. But in this case, again, I'm just going with the easy way. Now, because we're dealing with 32-bit application here, we need to convert from 64-bit size into 32-bit. Luckily, we can do it because we know that our size is, fits. So we just do with ulong and file size. Now, the way I call these things is just kind of like my way of naming the variable, so I can tell what it does and what the size of it is. Now, DW is double word, which is kind of like Microsoft way of calling a 4-byte or 32-bit integer. CB means it's a counter of bytes. It means it's in bytes. And file size, well, it's just a description. So in this case, we have to do cast and file size quad part. Okay, and then we actually have to reserve this. So what we're doing here, we're just reserving a large array of bytes from RAM. I'm sorry, from not from RAM, from obviously from RAM, from the heap. And again, make sure to free memory. And what I always like to do is also to null out the pointer, so you don't have any problems later if you start using it. Now this is kind of like doesn't do much for you, because it's like, well, you already deleted it, like why would you null it out? It doesn't do anything in C++. Well, by nulling out the pointer, you prevent it from being used further out. right? So let's say if over here you decide to write something into it, this will fail because this is null. If you don't do this, this will not fail, but it will create a problem which is called use after free, which is really bad. So please make sure to do this. And over here we again have to provide our error message. Now I'm doing kind of bad here because I'm copy and pasting it, and the copy and paste thing is bad because you can create duplicates. You see, like this string is the same as this one. There is no way the compiler can catch it. So if you are doing this, make sure to immediately remove whatever you added so it doesn't compile. It will later tell you to fill it in even if you switch to something else. So in this case I have to provide a meaningful error message. Let's say fail to reserve memory to read file, and the error code. Now unfortunately heap allocation doesn't return error codes, so we have to provide our own. In this case we can actually use a predefined error out of memory, and this will be shown to the user if the file is too large, if it's less than 2 gigabytes, and they try to load it and there's not enough memory available, virtual memory available for our process here. So okay, so at this point what we need to do is read file data into memory, and the way we do it is by using read file API. It takes file handle, it takes the buffer pointer where we need to read, it takes the variable of how much we want to read, and then returns how much it read, and we don't need overlapped. Now this little parameter here basically tells us, okay, you wanted to read this much, but I read this much. So we need to make sure that we actually read all of it. But before we do that, we again have to check for errors. Again, this is kind of redundant, and I see why people skip this part, because this is so difficult, to actually to actually do this every time, because you're distracting. You're like, why do I need to do this error handling? Because it's silly. Why would it fail? And you want to quickly throw in your code and make sure it works, but this part is very, very important. Now again, make sure to specify the meaningful description. Fail to read data from file, and in this case we need the last error code, which will be returned by this function. But what we also need to do is to make sure that what we just read is the same what we requested. In other words, if we read the entire file and not just like a small chunk. Now I know that this probably might not happen in many cases, but since API can return it, I want to check for it. Again, we're in a situation when we can't use get last error, because what we're checking is just this condition, which obviously doesn't have last error. We need to specify first the meaningful description, and let's say didn't read all file data. Now this will probably not happen, but it's just one of those things that you have to kind of envision and put a error condition just in case the API fails in this way. And this is very important, because if just some system somewhere in the middle of nowhere that you did not anticipate did not succeed in this way, your application has to handle it gracefully. Okay, now in this case we have a little bit of a dilemma. Now what error code do we use? So let's search. For instance, what if we search for partial, because we have some kind of partial operation here. Well, doesn't really fit well. Well, let's just use 707. Again, it's kind of like not the best way to do it, but it partially gives the user information that you know, it didn't take all of the data, you know, the partial data, so we'll stick with it. Okay, so at this point we have read our file into a buffer. Okay, so now what we need to do, we need to process our P header. Now, by processing, I mean that we need to look into it and actually see what is going on. Now, for that, I'm not going to create a long spaghetti code here. I will create a separate function. So let's just go all the way down here, and we will create it. Now, first of all, it will return the same exit code as we work with. And let's just call it for what it is, process, not PR, but PE file. Okay. Now, let's see, what does it take? Well, it takes a base address for PE header, which will be the top of our array that we just read into memory. Then obviously we need to know what is the size of memory that we just read. And well, at this point we don't know what else, so let's just add a declaration, and this is a static method again, and it is a protected, it shouldn't be revealed from the outside. And yeah, so let's write a little bit of comments, so for people that work, you know, after us, so that they know what this is. Now, this one is a pointer to the beginning of the P file. Now, the file, which is important, it should not be mapped. Okay, it's not memory mapped, it's just a file as we just read it, like if it's in the file structure. Now, this one is size of in bytes, size of this array in bytes. Okay, so I would say this is pretty much all we need. At the end, we will return one of our error codes. Let's just do success. If we get to the end, we will say that we succeeded. Because again, here we will parse our PE file, and if we don't succeed, we will just return error. Okay. Okay, so just for safety checks, because we will be parsing PE file, and again, in the first part, I wrote this diagram. So right now we're right here at address 0, and we will be going down this file and parse, well, not that far, but we'll just go down and parse the header here. Now, because we don't know which file was actually passed, because the user can pass us anything, it can be like a small file of like 2 bytes or just like totally different format, we have to make sure that we are parsing the right thing, and we have to put all kinds of error checks to prevent problems here. So for that, we will define an AND address. Now, the AND address is our base address plus size. Now, what is the AND address? Well, if you look at our diagram, let's say if it's our file, the AND address is here, which basically says this is our array. This is as far away as we can go. Anything outside will be considered an overrun. So we will have to be checking all of our offsets against this value, which is kind of important. Okay, so at first, let's do that specific check. We need to make sure that our size is, well, in this case, we'll do the opposite. So the size has to be larger than the first header, first part of the header here. And again, what I'm going for, again, I showed it in the first part, if you search for PE format on Google or, you know, with your favorite search engine, it will show this MSDN document. So, and what we're doing here, we're just going through like all this stuff, like DOS stub, like, you know, and what goes on. Now, it's a fairly large document, so make sure to familiarize with, you know, yourself with it. But that's what we're doing here. So the first thing that goes, you know, in front of everything is what is called image DOS header. So we need to analyze this thing. Now, if you go into peek view, it's kind of like not really large, but kind of like really old header that existed since DOS times in PE file. But for legacy purposes, it's still there. It's not really used for much except like this last parameter and the first magic number. But basically, it starts the PE header. So we need to check it. And the way we check it is we need to make sure that the file that we loaded actually has size, which is at least the size of a DOS header. If it isn't, we return an error. Right? We return, now we need to create a new error. Now in this case we have to, let's say next one, XC not PE file, and this is -3. Now what we're doing here, if the size of the file, now where is it? The size of the file is too small, it's obviously not a PE header. So we have to return it back to the user. Okay. Now this is important to do, and also important to make sure that this variable is unsigned, so that we also deal with very large values or negative values. In this case, they will not qualify because unsigned, like a negative value, when the variable is unsigned, it will be a very huge value, which will not pass. Actually, you know what? It will pass. So hang on, let's take a look at this. So in this case, we actually have to cast this size into signed value. So if it's negative, it will also fail here. So okay, now at this point we need to see how exactly we'll be calling this function, and the way we will be calling it is from here. So we will say that our result, which again result came from here, is something that is returned from a function, and we will pass our memory here, and we will pass how much we actually read. Okay, and then we need to process the results that the function returns, because we will not be outputting any user messages inside. This one is just kind of like a lower level function that will be just parsing PE header and return the result. So for this parsing, well, let's say if we do obviously success, oops, let's say break. Okay, success, we can just say all good, need to save new file with data from memory, because you know this function will adjust the memory for us of size bytes. Now we don't know the new size, so this function has to provide it for us, because obviously, you know, the size will be different, because again, if you remember the picture, we would have to cut out the end, the signature part, so the size will change. So let's do that. So let's say ulong UICB new file size. So, and this function will fill it in for us. And just as a precaution. We need to make sure that our size was actually provided for us. Because, you know, if it's not filled in, it will be still 0, and we can't save PE file with the size 0. So this thing here is just a sanity check, okay? Let's see. So at this point, we don't know any other errors, but we have to handle the situation when we, you know, didn't provide a default implementation here. Let's see if we go back and search. I usually like to do it this way, so I can just quickly jump. Let's see, path only. Yeah, unfortunately, they just put so much stuff in here. Okay, so okay, and we can return, okay, not PE file. We need to be able to handle this situation. And as always, we will use one of these things, except that we can't use getLastError because our function will not be using it. And now we'll address this. Like you see what I did, I removed it here. And by the way, I have to put similar thing here, because, you know, you have to always provide user with the error message. Again, by removing a variable here, I know that it will not compile, so it will bring me back to this line and I will correct it. Now let's just do it right here. So if we have not a PE file, we can just say specified file is not a valid PE binary. Okay, now error code. Now I do not want to use getLastError, but I still want to return it. So what we can do, we can actually create a variable that we will pass into this function. We will initialize it and then use it here to well, no, we can't use it here, to actually output the error. Okay, and now we have to address it in our function because we already have two variables that we will need to fill out. So if we go here, and so at first we have our ulong, which we will pass by reference as such because it will have to be filled in by the function, and new file size, and also we have our NOS error that also has to be filled in. Before I forget, we have to add these to the declaration so that the IntelliSense doesn't yell at me. And also we need to specify what these things are. This is very important for the next person that might be working with your code. And we need to write down receives new file size in bytes. Always write what the file size is returned in, because sometimes it may be bytes, sometimes it may be characters. After signature has been removed, let's see, valid only if result is success, because otherwise it makes no sense. And this one receives OS error code if any. So by providing these descriptions, the next person will be able to see, you know, what this is and how it's used. Now this is very important. Don't just leave it dangling. Since we used it here, we need to provide it here so that the function can actually fill it in for us. Okay. So we need to handle this situation. Our default, I would say that let's assume that our default is our failed to open. And in this case, we can use this. And then we can just say generic kind of an error. Failed to process specified binary file. Now we don't need a lot of description here because this is default, kind of like generic catch-all situation. So it just basically says, hey, something didn't work, and luckily we will be able to provide more information in here. Okay, well, let's make sure that I think compiles here. It does. Always look for warnings. In this case, we don't have any. And let's go back to our function that deals with PE headers. Okay, in this case, since we provided error code, we need to actually specify what the problem is. And in this case, there's a good predefined constant, which is bad exe format. That's exactly what the problem is. So again, in this case, we check the size of the memory that we got, make sure that we have at least DOS header here. And then if it's not, we return bad exe format and provide error code that our external function can handle. Okay, so then we need to define the DOS header itself. So, and the way we do this is just by doing this kind of thing. So DOS header, I usually call my variables somewhat understandably so you can at least, kind of see what they are. And what we do is just, it's right on the top, right at the base. Okay, so the next thing we need to do, we need to actually skip it. And the way you skip it is just this last offset. And the way you do it, we need to get its size, because again, what we need to see is that we do not go over, because with all these offsets, it's very easy to go over the stuff that you read, the array that you read, and go over and create very nasty buffer overflow. This is very important. So what we're doing, we have a let's see, this plus size of image and T headers. Now what I'm doing here, let me explain real quick. If I type it right, and I need to cast this into unsigned. I'm assuming the worst, let's see, worst case or 64-bit PE. Now, what this means is that, okay, now if you read the documentation for PE header, you would see that this is the next offset to what is called NT headers. Now, because there are two versions of PE headers, the 32-bit and 64-bit, we have to assume and account for that as well. Now, obviously, 64-bit headers will be larger than 32-bit headers. That is why I'm assuming the worst case, okay? So what this does, I'm skipping till the end of DOS header to where NT headers start, and then I skip the size of NT headers. And in this case, I'm assuming the worst case, the larger one. Okay, now we have to do again the same kind of a check. So if this is actually larger than our memory, we return an error. Now we can return similar thing, because we just just tell the client that, hey, bad file, bad PE file. Okay, so next step is to define NT headers. And what we do, let's see, well, we don't need at this point because we were using the lower part of the header, so we don't care which header it is. Let's see, put NT header. Again, now guys, this structure you can get from the document, the description of the PE format, so I'm not going to go into details here. So what is important is that we get to it as such. And basically what we have is, again, is the base address plus ulong size here, and we get to the headers. We need to make sure that this is the actual NT header. We can check the signature, and the signature is image NT signature. If not, we go back to the same error, not PE file. Okay, now this is important to make sure that the person doesn't pass some kind of like file that is not PE header. Okay, so now we need to get to sections in PE header, in PE file. Now sections, I'm sorry, not to sections. Yeah, to sections in PE header, not the. It's very confusing. They call sections pretty much everything in Windows, but these are sections inside the PE header. So, and what we do, again, we use internal section header structure, and let's just call it, for the lack of a better name, sections. And what we will use is a special macro that Microsoft very thoughtfully provided for us. So it's a built-in macro. If you want to see what it does, it has a little bit of finagling here, a little bit of manipulation, but it basically takes us straight to the PE sections. Okay, now at this point we got an address, and we don't know where it is. It can be well within outside the bounds of our structure. That is why we need to check it. Now, for this kind of a verification, I prefer to write a special macro. Now, I know that macros are kind of dangerous, but in this case, you know, you have to be careful, and basically you need to know what you're doing, and that's what we will be. I would call it check pointer for overrun. Oops, not overrun, but overrun. Now we have pointer to structure and AND. So let's see, what does it do? Well, it casts our pointer to byte pointer and checks against the AND. So if this byte pointer is greater than the AND of our array, or equal, by the way, because it's the AND is kind of like 1 byte after, or again we have to cast our pointer into byte plus the size of our structure, because it's a pointer, we have to do this. If that is also greater than the AND, then this is an overrun. Okay, and now we can use this thing into, not here but in our class, if we say if check for overrun, and what we have is our sections pointer against the AND address that we calculated before. So if that happens, we are again not dealing with the PE header. Okay. Okay, well, at this point we can be sure that we are inside the image section header, which is what we need to do our further verification. So now we need to determine the bitness of our PE file, and also get some other info from the headers, which we will need later. Okay, Now the way we check bitness is by using NT header structure and something which is called optional header, which is not really optional, and we use what is called magic. I know, really bad naming, but that magic has special magic constants, which is NT optional HDR32 magic for for 32-bit. I'm going to copy and paste obviously 64 for 64-bit. That's how we can tell which PE header, which PE file we actually are dealing with. And always remember to handle defaults. In this case, we are not dealing with the PE file that we want to deal with. So return an error. Okay. Now, in this case, we will need to keep couple external references. Now we need 32-bit header. Let's just call it PNT header 32. Initialize it to null originally so that we can catch errors if we don't initialize it later. And then we need to cast our header to our 32-bit header in this case, right? And what we also need to do, we need to get to the something called image optional header. In this case, we know it's 32-bit, and let's just call it, I don't know, IOH32, which is the pointer reference to optional header. Okay. In this case, we also need to check for overruns on our header, which is important because, you know, if it's pointing somewhere outside of our structure, that would be a problem. And if it does, just do the same thing, just return error. And also, what we actually need to get to image data directory. Okay, and let's just call it data directories. It's actually multiple because there's more than one, and that's where we need to get. So at the end, we just say that this is our, oops, not this one, this one. And this is data directory, and that's what we need. So that's how we calculate. So again, we need these directories to actually get to the signature. And now 64-bit is very similar, so I'm going to just copy and paste here. Now this one is 64. Let's add it here. Now with copy and paste, again, it's very easy to make mistake, so make sure to watch that. So make sure to cast here. We have 64, 64, doing 64. Make sure to check for overruns and get pointer to our directories. Okay, so at this point, make sure it compiles. So we haven't made any errors yet. So we get pointer to our directories, and let's make sure that we got, let's just call sanity check, not sedge, but check. Make sure that we got directories here, that we didn't like forget to get it somewhere. Okay. And so now we need to examine something what is called, I think, image directory entry I'm using IntelliSense to help me. Security. Okay, we need to examine this one. So how do we do this? Well, first of all, we need to get to it, and the way we get to it is by using this constant. Now, if you look at it, it's index 4 in our array of directories. But before we can actually use it, we need to make sure that it is within our bounds of our array. Again, don't forget to check the bounds of our file here, because again, the user could have passed pretty much anything for us. So we need to again do this kind of check here, and we put image directory and check against end address, and if it's outside, we fail. Okay, we just return no, not a P file. Okay, well, next thing that we need to do, since we have the image directory, it will be empty if there is no signature, so we need to see if we have any signature, and this one is really simple. We just use our image directory, and we need to see that size is 0 and the address is 0. In this case, this is no signature. Oops, signature. Okay, now we need a new return value. Now in this case, it's technically not an error. This is a warning, I would say, and we would say XC binary has no signature, and I would set it as 1. And that's what we return. There is no need to do anything. It just says, hey, no signature, don't have to do anything. Okay, so then we need to make an assumption that signature is at the end. Now, like I said, this is not entirely documented, or I didn't find it, but most, like all the examples I saw of signed files, the signature was at the very end of the file. If that's not the case, we will have to modify it here, and that is why let's make an assumption and a check. First of all, let's make a comment. We will assume, assume that the signature is always at the end of the binary file. Okay, now how do we check that? Well, let's just say that if we take our virtual address, by the way, which is not Microsoft stepped away from the usual definition, and instead of providing this address, they provided offset in a file. So this is what this is. So if we add this to the size, if that's not our size of array, if you remember, we got it here, or the size of our file, if that's not it, so the signature is not at the end of file, right? So in this case, we need to return another error code. So let's think about that. So in this case, we have, let's see, XC, let's just call it bad signature, which will be -4. Okay, so we can use that and return it, but also, because this is an error, we have to return an error code. But in here, we actually need to find a suitable code. Since we're dealing with signature, and make sure I can spell it correctly. For some reason, I have problems with that now. Let's see, what can we pick? Well, how about this one? An error encountered while processing. Okay, well, XML, but let's ignore it. Digital signature. Seems like the right match. Doesn't have to be exact match, because again, there's like a certain limit of error codes that you have to play with, but that seems to be something that should work for us. And we return it here. Now what's important is that this value, this is bad signature, and we cannot work with it. Okay. At this point, we can, let's see now, start modifying the binary, because we made an assumption that we can work with it. It's at the end because of this line, and we know that there's a signature in the PE header in a image directory entry security, so we can just start modifying it. So first we need to remove digital signature from the PE header directory. So what we do is very simple. Just null it out. Size is 0 and virtual address is 0. This is very simple. The first thing, actually, we need to set new file size. In this case, we are using this new file size that we were passed in. Remember, it's only valid when we return success, so that's why we do it here. This is very simple. It's just an offset here. So offset to the beginning of signature. So we just set it to new file size. So this means that the file will be cut off right here. And another thing that we need to do, we need to calculate a checksum. Now the checksum is something inside the PE header. Again, if you, let's see, checksum, if you search for checksum, you can, it will tell you, where, let's see, like an optional header has this checksum value that is kind of like a very rudimentary, very old checksum on the file, but it's still used. It may still be used, and because we modified the header and because we provide a smaller file size, we have to modify, we have to update file checksum. Now luckily we don't have to do it ourselves. If we search, there is an API called checksum map file. Kind of weird name, but what this does, it calculates the checksum for us. Now we need to provide a couple pointers for it, and the main one, we actually have to know where the checksum is. Now for that, we can go back to our optional header, because again it's an optional header, as you can see from here. We need to get the pointer to it. Okay, now the checksum is just a D word, as Microsoft calls it, so let's just get a pointer for it. Now originally it's null, and let's do an assertion here and actually make sure that we provided it. Now the reason I do it here is so that I don't forget. If I modify something here, or if somebody else modifies code or puts like an if statement, it will not fill in the checksum. So this is important that we do this, just to check, like a sanity check. Okay, so now we need a pointer to it. So we get this pointer from the optional header, and it is called checksum. And we do the same thing for the 64-bit header. Okay, so now we have this checksum pointer that we can update with the call to our API. And then if you read, what exactly it does, so it calls. Before we can call it, we actually need to oops, not open link. We need to copy it, and we need to add, well, let's say here, we need to add an include for the library, and what we also need to add is the library, static library itself, so that it can actually statically link it. Now I will use a well, let's see what is the best way to do it. I would probably, yeah, let's use it this way, pragma comment, so that we can keep all of it in the source code instead of using the properties. I would use it this way. Okay, so now we can call this function. It takes, well, takes the base address. What this does, it basically tells it the beginning of the file, takes the new file size. We have to specify this because we just, you know, we're just passing just, you know, one, just a chunk that we, you know, cut off. I mean, the one that cut off and wasn't present. Now we need to provide original checksum, and we need to provide new checksum. We null them out. First we provide original checksum, and then we provide the new checksum. Now read the, you know, the documentation for the API, what it's doing, and then it will return an image header. Now if it returns null, it means that it failed to compute new checksum. Now in this case, if we look at the API, it returns get last error. So we can actually use get last error to return it back to the user, and we need a new return value. Now return value is something that we need to add. That's just called failed, let's see, failed checksum, right? Just make something simple, -5. And we can put it here. So if we fail to generate our checksum, return. Okay, and now all we need to do is to set new checksum in memory. Because right now it's just stuff in memory. We don't really have a file yet. We have a pointer though. And, oops. As always, make sure that the pointer is set. And let's see, obviously we set the new checksum. Okay, well, in this case, at this point, this is all we need to do. So we got the checksum, we updated an RP header, we updated the, you know, removed the signature in the directory, and we set the new size. So let's make sure it compiles. And it does. So at this point, what we have is our file, I mean not the file, the memory array that has been modified. So let's go back to where it's used. And in here, we actually forgot a couple things. Since we added new return values, we need to make sure that we process them here. So let's see, what did we get? We get bad signature. We need to put it here. Let's just do it this way, break. And then we had failed checksum. Oh, and actually we also have this one that we add, and there is no signature. So all this stuff we have to output to the user, because again, all we have is just this value. Okay, failed checksum. No PE file, we got this, bad signature, and failed checksum. Now the way we can catch these is by having this assert statement. So if we get here at the default and we don't have implementation for it, it will assert for us. So it will tell us that we need to add them. So let's do it right now. So let's see. Okay, this one, no signature is a little bit different. Now bad signature. Let's just say specified file has incompatible digital signature. Okay, and here we would say failed to create, let's say to compute a checksum on the file, on the new file. Okay, and lastly, we need to process this thing. Now in this case we can't report an error because this is not an error. So what we need to do, we just need to output a regular message. Basically says, let's see, binary file has no digital signature, and we specify which file and the new line. And the new file is this. Okay, so let's build it. Okay, and it builds. So at this point we can handle all the errors here with proper messages, and the only thing we have left is to handle a success. Now we get here, if we modified our file memory, so we removed signature, we set new size, and we are ready to write the file back. Now the thing is, I wouldn't be writing it back into the same file because, you know, obviously you don't want to override the original. So we just need to create a new file. But for that, let's set new file name. Okay, so first I would, let's say, define a suffix file name. Let's just put space, no sig, something like really simple. And let's just add to file. So whatever the file name is, let me explain. So let's say file.exe. We will turn it into file nosig.exe. So that's kind of like the thing here. Okay, so first we need to, let's see, find out the length of the file name, and let's use CRT function. So we have the file path that was passed to us. Then we need to see size chars, length, new file name. I prefer to give my variables kind of longer names so that we have, you know, so we know what they are. Now we need a file name plus 1 character, and we account for terminating null. Always remember this. That's why we add 1, because this function will not account for terminating null. Plus we need to add the size of this. Technically you can just count and just say whatever the count here is, but I don't like doing this. I personally like to create a small preprocessor definition that will do it for me. Let's call it size of text for t, and what it does is very simple. It just does count of t, but then it subtracts 1. Here it removes last character. So now if we go back, we can actually account for our suffix. So this will give us the new length of the name. So since we don't have specific length, let's just reserve it from the heap. And what we do here is this. Obviously this can fail. Handle errors and free memory. Again, doing the same thing immediately, making sure to null it out, because this is very important. And then we have an error. Now an error, something that shouldn't happen, and we can actually report it. Now the reason I put assertions here with false is because this should almost always succeed, because we're not dealing with huge memory allocation here. So if for some reason this fails, we should know about it right away. Okay, so the error message is error out of memory. Now here, what we're dealing with, we are specifying error message for the user. Fail to reserve memory for new file name. Again, don't assume that this will never happen. It may. Okay, so right here we actually did all of our reservations. We returned memory back. But then let's find extension. And for that, now we need to add a new function, which is called path find extension. Again, it's Win API, and it lives in shell WAPI. So we go back here and we do exact same thing. And we also need to bring a lib for it. Oops. And the lib is this. Oops, need all of this. So now we can call path find extension, and we provide our file path here. And let's see, I'm just gonna create just quick variable. It will be all optimized. So now we need to see extension offset, which will be our extension minus this. Now the reason I'm creating this little local variable so that I can debug it in case there's a problem. I just don't want to put this here, because then it will be kind of like not very readable. Now we need to make sure that we're actually calculating stuff correctly and our offset is not negative. And then lastly, we need to make new file name. Now I'm going to use safe string printf provided by the library, by the Win API by Windows. So we need to provide our buffer, which we just allocated, the new length. Then we need to provide what we're doing here, because again, this is a printf statement, so we'll provide specifiers here. And let's do it now. So at first, we need to provide a string with the length. Oh, sorry, not this, but this. So this little star and dot will allow us to provide how many characters we have to take. And that is the offset to extension from string file path. So that's what this will take. Then we put a suffix. Let's just do it here. And after the suffix, we put our extension, which is string file path plus offset to extension. Okay? Now we need to make sure that all of our stuff here actually works. So in this case, I'm not going to do an assert. I will actually check for the error message, and I would say if whatever we just did above succeeded, we can go ahead. Otherwise, it's an error. Again, don't ignore it. This is very important that you make it right. And in this case, we can do the reporting again right off the bat. I delete this, and let's provide kind of like basic description for the user. Failed to make new file name for, and then here we need to cast our HR into an int. And you know what, in here I will also provide an assertion, kind of like a fail always assertion, so that we can catch if our stuff here didn't really work. Okay, so at this point we have our file name, which is what we needed. So now we need to create new file, and what we do is just we use create file, same API. We use new file name. In this case, we have generic read, but not just generic read, because we're writing. We'll also have generic write. We will make it not shareable, no security. We say create always, meaning it can overwrite existing file. File attribute normal, and no template. Now in here we need to have new handle, and as always we have to make sure that it worked. Error and close handle. Close handle. You see I'm doing this right away. I'm putting verify just to make sure it worked. Now error would be indicated by invalid handle value, and the error here is something that we have to type in. Immediately remove this, and let's write some meaningful description for the user. I would say failed to create destination file. Now in this case we have to provide new file, not the existing one. And here we can actually use get last error to get an error from this API. Okay, so well, now it's just a matter of technique. So we have to write our, let's say write into file, and we use write file API. We have to use file2. The buffer is file mem. Let's make sure. Yep, that's file mem that we worked with. Now the size is new file size. Remember, we're cutting off stuff. Then the API will return how bytes were written for us, and null. So we need to create a dword for that. And again, this is just the way for the API to tell us that, hey, that's how much memory I wrote in. And let's see, we need to again catch all the errors. Now this is important again because it can quite easily fail. And here we would say fail to write to destination file. Okay. Now also at the end we have to make sure that we actually wrote as much as we wanted to. Again, this is important. Make sure all data has been written, because again the API might write just a small portion, you never know. And in this case we have to provide an error. Unfortunately we can't use get last error. And let's see, fail to write all data to destination file. So the challenge for us again is to see, which error code to return. Let's just search for, I don't know, write. Well, like for instance, generic one, write operation. Let's use that one. And we put it here. So now, when we know that everything has been written to the file, we can pretty much say that we are all done. Okay. Now in this case, our result. Okay. Now this. Okay, we have to go back and actually adjust something. Now, if you look at this, the result that we have here is already success, but we can still fail. So what we need to do before we actually do anything here, we need to assume failure. And for that, we need a new error code, and that is XC failed file write. And what this tells us is that, okay, we calculated, we did everything, but we failed to write to a file. So it can be returned, to the user from the process. But in this case, we actually have a success. We have done everything and it's been written. Now, just as a courtesy for the user, let's output it as a message. We're going to say success, creating new binary file without signature, and I'm going to put a new line, and in quotes I'm going to put a file and put another new line, and then at the end we are going to say which file was created. Okay. So at this point, let's make sure it compiles. At this point, our function actually works and outputs a file, so we can use it. So now we just have to do a couple cosmetic things to make it run and make it work. Now I see that this video is kind of long already, so what I will do, I will stop and I will finish it up in the last section to kind of do the last final touches before we can actually publish this application. Okay, well, thank you very much for watching. This was part 2, and I will see you in the next part.